So as promised, I am presenting you with more examples of metric spaces, and I will try to draw on examples that appear in current and active research so that you get a flavor of what working in this particular area of mathematics feels like and what kind of things you should be prepared for. I want to talk about this second paper of mine with my PhD advisor Piotr Hajwasz, titled Lipschitz Mappings, Metric Differentiability and Factorization Through Metric Trees, which has been accepted in the Journal of the London Mathematical Society. In particular, the reason I want to talk about this is that I will talk about, of course, my papers at some point in more details, is to introduce you to the notion of metric trees. So the main question in this paper was, if you have a function f between two metric spaces x and y, when can you plug in a third metric space z so that you can break f into composition of two Lipschitz maps by first going from x into z and then coming from z to y? So why would one want to turn a single map into two maps? The answer is that often we wish to find a space z that is kind of a simpler space or more universal space. And in this particular paper, we wanted to know when you can plug in this z, and z is a metric tree. So we will talk about metric trees, and we ended up finding a bunch of equivalent conditions, and that was a nice theorem with many also sideline results that were of independent interest. So the main theorem says that if you map from the cube into a metric space, there are no restrictions on the metric space, by the way. If this map is Lipschitz, then you can factor f as I described above through a metric tree, which will be our z, if and only if one of the other conditions here holds. If the rank of the derivative of f, of course this derivative is not your typical calculus derivative, as x is only a metric space, but there are ways we can put meaning to this. If the rank of the metric derivative is less than 1 almost everywhere, if this density, which is kind of a Jacobian, is 0 almost everywhere, and the other quantities are also some metric quantities similar to this h2 and h2 hat, are quantities very, very similar to how Hausdorff measures are defined. And we say that the function will factor through a metric tree if and only if these quantities are 0. So how many? Say 5 equivalent conditions to when you can break a map into factoring through a metric tree. Okay, of course I don't want to talk about the main result of the paper. As I said, I want to introduce you to the notion of metric trees. Okay, so a metric tree, or also called an R tree, R for the real line, is a metric space that is geodesic, first of all. That means between every x and y, there is a curve whose length equals the distance of x to y. So Euclidean spaces are geodesics. The surface of a sphere is a geodesic. Now, I mean, if you equip it with the right distance, right? We have talked a lot about this in the curves on metric spaces thing, because this concerns curves. So we start with a space that is geodesic, a metric space that is geodesic. Then we call it a metric tree if any of the following conditions is satisfied, because all of these conditions are equivalent. So let's see, for any x and y, there is a unique arc with endpoints x and y. So an arc will be an injective map from an interval. It has no self-intersection. And we can take it to be the geodesic connecting them. By being unique, that means if you fix two endpoints x and y, there is only one way of getting from x to y. So this here arc is by uniqueness, that means it's not unique among geodesics. It's unique among all arcs that connect the two. Okay, actually there's the precise definition of arc right in the paragraph that follows. So an arc is a homeomorphic image of the unit interval. So it's just a continuous map from unit interval into the space that is also injective. I think injective will be sufficient to say that the inverse is actually also continuous because 0, 1 is a compact space. The second condition, which again is equivalent to the first, is that no subset of X is homeomorphic to S1. So these are so far topological things. We're not talking about Lipschitz images or by Lipschitz homeomorphism. It's just homeomorphism, continuous with continuous inverse. So this number 2 basically says that there are no loops in the metric space X. So let me draw a couple pictures of these, and then we can move on to the next thing. So the naive picture in our minds that we have a metric tree, well, is that it's a tree. So what is special about a tree? You branch out and you never come back, you never return. So the second one that says there are no homeomorphic copies of S1 in there, so that means this never happens. If this happens, then there is a copy of S1 in there. So there's no looping. And it's easy to see why this is equivalent. This has to be equivalent to having unique arcs. So suppose there is X here. Okay, suppose there is X here and there's Y here. If there were two arcs, two homeomorphic images of the unit interval connecting them, so let's say this is another one, then from these two you can find the circle. So the cheating picture will be that, well, there's one arc and there's another arc completely different from that, but if you put these together, then from them you see a copy of the circle. And also, if there is a copy of circle, vice versa, if there is a loop in the space, you fix X and Y along it. So there's one curve going that way, another arc going this way. So again, it violates uniqueness of the arcs. Okay, so very reasonable. Let's see what other equivalent conditions are given. X is simply connected. You can move every loop into one point and just and the topological dimension of X is 1, so this is a more complicated thing. Every geodesic triangle is isometric to a tripod. The other conditions I won't come back to because they are more involved and technical. Actually, in the paper we use condition G because we want to connect it to derivatives and analytic quantities. But let's talk about condition D. So every geodesic triangle is a tripod. So what is a geodesic triangle in any metric space? So you will have 3 points. Now a geodesic triangle will be, you find one geodesic from X to Y, like the shortest curve. Another geodesic between x and z, and then the third geodesic is from y to z. Or you could also have this, for example, in the Euclidean space. They are all not always technically triangles, they could be collapsed. So you could have this situation. So the shortest curve from x to y is this, the shortest curve from y to z is this, and the shortest curve from x to z happens to be contained in just the union of the previous ones. As you can see, such an example cannot be a tree because we have a loop. So how can we avoid having loops? The only way is for triangles to look either like this or this. You have x here, y here, and z here. So shortest curve from x to z is this. The geodesic, which by part A is unique, there's no other shortest curve from x to z. From y to z goes like this. And then the shortest curve from x to y happens to be just making this turn half big. So this and this are the only allowed formations of geodesic triangles. Of course, x, y, and z can change the letters. So without loss of generality, this is the only possible configurations inside a metric tree. So that condition being equivalent says that if in a metric space, all your triangles look either like this or like this, then your space is also a metric tree. So as I said, this is a naive way of visualizing metric trees because metric trees can be indeed violent and huge. Their topological dimension is always equal to 1, as was seen in one of those equivalent conditions. But their Hausdorff dimension can be as large as we wish. And these trees have been used in a lot of interesting constructions in analysis. So one of the very famous examples by Kaufman from 80s is he built a C1 map, continuously differentiable map, from the cube onto the square, 0, 1 to power 2. Okay, so this is f is in C1, has continuous derivative. Now you may say that if a map covers all of this squares, so it covers area, so at some point its rank, its derivative must be full rank, right? But the example Kaufman made was that this is actually less than or equal to 1 at every point, because you have continuous derivative almost everywhere, will just be everywhere. So at every single point in the domain, the derivative has rank only 1, so that means the derivative does not vanish at most in only one direction, and in the complementary direction derivative is 0. This example was constructed using trees because trees are basically one-dimensional, and that direction in which the map does not vanish is when you have branchings of your tree. So how did and you can see that the way Kaufman constructed this, and that example was motivation for study of when you can factor through a tree, right? So when can your f go into a tree and then come back? This example actually was the main motivation behind considering that question. So the way he constructs his example is most of the cube, in fact, just goes into a tree. So you put initially finite iterations, so you build these trees, and then at every step you add more points, more branchings. What happens is that ultimately the set of these nodes, let's say, that you get to becomes a dense subset of the square. And when you take limit, all of the square gets covered. But there is a null set inside here which does most of the covering, and the rest of cube, in fact, just gets crushed into this topologically one-dimensional tree. But again, that's an indication that the Hausdorff dimension of the tree can be large. In this case, it's 2, and although this topological dimension remains 1. So trees are not really simple graph theory combinatorial trees. So metric trees can still be quite complicated. And as you can see, they can be used to construct a lot of things. Notice that this condition was in our main theorem that a map can factor through a tree if and only if its rank is less than 1. And this is in complete agreement with that. And that was also how this was conjectured, that if you have rank less than 1, you can then factor through a tree. And what we did in this paper was we, in fact, constructed this tree almost by hand using some previous work in literature, and we gave a way of, so we had the map f that went from x to y, and we succeeded in using structure of y and x and f, and of course the assumption of rank less than 1 to construct this tree, and then prove that there are Lipschitz maps this way and this way, which make this diagram commute. Yeah, so metric trees, very nice objects and very important in metric geometry and Hausdorff measures. Okay, I'm trying to recall if there are some other amazing facts about trees. There are definitely, but a simple example that I can give you in 1 or 2 minutes, maybe not. So maybe I'll keep other interesting examples of metric trees and what you can do with them to some future videos. Thanks again for tuning in and listening. Please put your questions down in the comments if you have encountered metric trees before, or R trees as they are called, or happen to have a favorite fact about them. Again, please consider putting that in the comments. Thanks a lot and see you soon.